Today we'll be looking at planes, but not your planes that you're going to travel to China in, but the planes that are like a sheet of paper or a wall. These planes go forever, unlike planes that run out of gas. So a plane in Cartesian form, in XYZ form, has an equation of ax plus by plus cz equals d. In vector form, if you look at the picture here, we have two vectors within this plane, b and c. And it should make sense to you that to define a plane, to define how that plane is slanted through space, or the angle that it goes through space at, is determined by 3 points. And by extension, by two directional vectors. And then a point in space also will tell us where we start the plane. This is a lot like the vector equation of a line. We have a point in space, a vector, plus some parameter times b, plus another parameter times c, and those three things added together give us our vector form of a plane. So let's use that. We have 3 points, a, b, and c. We're going to use point A, vector AB, and vector AC to write an equation for the plane passing through these 3 points. Now, it's worth noting that it doesn't have to be these three things. We could have used point B or point C and any combination of these 3 points to come up with direction vectors. But I'm choosing to use these three, so you're going to do it also. You don't get a choice. Let's try to work through this together. First thing first, we need to find vectors AB and vector AC. Pause the video and find these two column vectors. We should be getting -2, 1, -1, and for AC, -1, 1, -2. So now we have our point and our two direction vectors. Our vector equation is simply going to be 1, 0, 1 plus alpha, some parameter. It doesn't matter what you call it. It doesn't have to be alpha and beta, but alpha times -2, 1, -1, plus, I'm going to change the world on you. We're going to do lambda times -1, 1, -2. And there is our vector equation for this plane. But you know what? That's great. That's fine and dandy. But how do we get to the Cartesian form? That's something that we want to know how to do. We don't necessarily want to keep it in vector form. So let's write the parametric form. We're going to start with that. And writing the parametric form, remember vector r is x, y, and z. So x is equal to 1 minus 2 alpha minus lambda. Y is equal to 0 plus alpha plus lambda. And then the z component, its parametric piece, is going to be 1 minus alpha minus 2 lambda. Okay, so there are my parametric equations for this plane. It's another way that we can express an equation for the plane. But again, I don't want parametric equations. I don't want this in terms of alpha and lambda. In terms of those two parameters, I want x, y, and z. I want it to look like what I have highlighted in yellow. And that's where we're going to get to, but it's going to take a little bit of work. So here's what we're going to do. We're going to take a pair of these equations, and we're going to solve for, or we're going to eliminate one of the parameters. And then we're going to take another pair of these, and we're going to eliminate the other parameter. So I'm going to take equation 1 and equation 2, and I'm going to add them together. I'm going to eliminate lambda. So I'm going to take x equals 1 minus 2 alpha minus lambda, and I'm going to add to it y equals alpha plus lambda. And adding them together, we get x plus y is equal to 1 minus alpha. Okay, so what I can do with that now is I can say, okay, anytime there's an alpha, that's the same thing as 1 minus x minus y. So now I have a way to eliminate the alpha from my equation. Cool. Now I need to eliminate my alpha. Or I need to be able to substitute for lambda, meaning eliminate alpha. So I'm going to take equation, I don't know, it doesn't really matter too much, but I'm noticing that equation 2 and equation 3, I can add those together and the alpha will cancel out. So I'm taking my y equals alpha plus lambda, and my z equals 1 minus alpha minus 2 lambda. I'm going to add them together. We get y plus z equals 1 minus lambda. So lambda is equal to 1 minus y minus z. Okay, so these are two big important equations for us, big relationships between our x, y's, and z's and the two parameters, alpha and lambda. So what do we do with them? Well, we're going to take them and plug them in back up here, and it doesn't really matter which one of these three things we substitute into, but I'm going to substitute into one of the three parametric equations, and I'm going to see both of those parameters disappear, and we're going to get the x, y's, and z's all on the same side of the equation. So I want you to pause the video and do that. Make this substitution into either equation 1, 2, or 3. Pause it now and give it a try. All right, I am going to substitute into equation 2 simply because it says y is equal to alpha plus lambda. It's less work, more efficient. That's what I'm all about. So y equals alpha plus lambda. And collecting like terms, moving all of my variables to one side, my constants to the other, we get x equals x plus 3y plus z equals 2. Whew. There is the Cartesian form. And maybe you're saying, gosh, I sure hope there's a shorter way of doing this. And once you know, there actually is. So we're going to do a little exploration here. We're going to take the two directional vectors, AB and AC. We're going to find the normal to the plane by doing AB cross AC. Pause the video right now and find the cross product for AB and AC. And doing this cross product, you should get negative I hat minus 3j hat minus 1k hat, which in its column form would be negative 1, negative 3, negative 1. And if you notice, that's a scalar multiple of 1, 3, 1, which, even more importantly, is a vector that consists of the coefficient of our Cartesian form of this plane. So that's a big idea. That's huge. So if we have a plane and we know the normal ABC, and we have a point x0, y0, z0, let's develop a shorter, nicer way to get this Cartesian form. So it should stand to reason that any vector in the plane, for instance, that vector, will be perpendicular to a scalar multiple of the normal. So putting that into words or into mathematical symbols, the dot product of the normal and the vector green one that I have drawn here, x minus x0, y minus y0, z minus z0, needs to be equal to 0, where x0, y0, z0 is a point in the plane, any point in the plane. So if we write this out, n1, n2, n3, that's our normal. Those are the three components, or ABC, if you will, times our x minus xo, y minus yo, z minus zo, and expand this dot product, look at what happens. And doing a little bit of rearranging, we expand, get all of our x zeros, y zeros, and z zeros to one side and x, y, z on the other. We get n1 x plus n2y plus n3z equals n1 x0 plus n2y0 plus n3 z0. And that's simply the dot product of the normal and a generic xyz point, equaling the dot product of the normal and that point in the plane. And this, ladies and gentlemen, is some high-powered stuff. You don't have to go through solving that system to find the Cartesian form of a plane, and let's do that in an example. So, find the equation of a plane pi, which contains the point A and is normal to this vector. Well, to get this equation, how do we do it? Well, glad you asked. We're going to take the normal, 2, negative 1, and dot it with x, y, z, that generic point in the plane, and that's going to equal the normal dotted with our point. Because that point's in the plane. Now we expand. We get 2x minus y minus z equals negative 2 minus 1 minus 2. So our Cartesian form is 2x minus y minus z equals negative 5. And dot, 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 we are done. And that's where I leave you. In the next couple videos, we start talking about how lines and planes intersect each other and how we can find the angles in between them where they are intersecting.